All right, so this is week 3, and this week I talked about our, I guess I learned about PCA, I learned about k-means clustering, natural language processing, and I think it was called recommender systems. Um, those 4 topics that I kind of just discussed didn't go super deep into them, just learned a little basic programming, how to apply them into Python. But mostly this week I've been focused on something called support vector machines, SVMs, right? And more specifically, it's the support vector classifier. So support vector classifier, it's super good for classifying between usually binary, so like A or B, true or false, where there's only 2 options and you pick one of them. Uh, but with the given correct parameters and stuff like that, you can obviously adjust it to be more than just a binary classifier. It could be 3, 4, or however many you want. So let's talk a little bit about the support vector machine and what it does. So we have this. So first thing I want to discuss is um, why is it called support vectors? Uh, so let's say I have some points here, and I have some points here. It's pretty easy to find distance or find a separator, just by looking at this pictorially, you can see, hey, there's a pretty easy way to separate this. I can draw a line here to separate it. I can draw a line here to separate it. I could draw a line here to separate it. It doesn't matter. There's an infinite amount of lines that I could draw to separate these. And I can always say that if I draw this line correctly, the green points will always lie to the right of the line, and the red points will always lie to the left of the line. Okay? But what support vector machine does is it's going to maximize what is called the margin distance. So if you notice right here, when I draw this line, I have, I can draw this support vector here, and I can draw another support vector here. That's actually a poor example. Let me just display this right here. So I'm going to draw something like this here. Okay, and this is what's going to maximize the marginal distance. What is the marginal distance? It's basically the distance from one of these points, the closest point to the line, and then we're going to draw like this kind of outline, this shell for this, and this is what is called the margin distance, okay? And we want to maximize that. So this may not be obviously the maximizer. I may be able to draw a different better line, but that's, for the computer to solve. I just want to discuss the intuition behind it. And so what's going to happen is these 2 points, this point right here and this point right here, are called support vectors. You may be wondering, hey, why is it called support vectors? It's just because every single point can be expressed as a vector, whether it's in a 2D, 3D, whatever. So let's say I have this point. Maybe I just picked this green point that I was just talking about, and I draw this line right here. This is a vector, right? So we can pick this to be x and this to be y, and this is the vector x, y. Okay. Um. So now, um, this works super well because there's a clear distinction, and you can draw one linear line down the middle, or however you want to draw it, and you can have a clear indicator. The reason why this is so beneficial is because this is really good for extreme cases where 2 products are very similar, or 2 things that you're trying to classify are fairly similar. So for example, let's say you have 2 different brands of shoes. I don't know, Nike or Adidas, sure. First 2 things that come in mind, and happen to have to the shoe. Their shoes happen to have a very similar color scheme, right? So maybe that could be represented from this point and this point here, right? They're very close to this line that separates it because their color scheme are super similar. So of course they're going to be really close to the similarity charts. That's where they're going to be. The 2 points are going to be fairly close to one another compared to maybe this point, where we can have like a super blue and dark shoe, and then this point right here is a super bright shoe. Sure, whatever. For 2 different brands. But now these 2 brands happen to have a shoe or 2 shoes that are very similar to one another. So what's great about this is that this is extremely good at classifying the difference between the 2 because um, you have this line, this clear separator that separates between the two. It's very clear. So let's say I have, I don't know, maybe this point right here. Well, this is to the right of the line, so we're going to classify this as the green category. And then maybe I have something like here, down here. It's falls to the left of the line, so we're going to classify this as the red category. Okay. Um, so with support vectors, um, I've been talking about it in the terms of a line. This is a very two-dimensional way of thinking this, but in reality, if you extend it into, higher dimensions, it's referred this separator is referred to as a hyperplane or just a plane. Okay, so this works really well when you can separate this. This is when we use, if you take a look at this, it's called a kernel, where we use a linear kernel to separate between the two, right? It works super well because you can clearly, like I said, I've been, I guess, repeating myself, draw this line. It's a linear line that can separate this. Now the problem presents itself when you cannot separate it linearly. So this is the case with something like this. So don't worry about this. I drew this earlier because I failed an earlier recording, but basically if you take a look at this, where it's a red circle kind of, uh, with a green circle outside, it doesn't matter how I draw this line. I can try to draw this line here, draw this line here, but you can see that no matter how I draw this, there's always going to be both green on the left and the right, or the top and the bottom, depending on what perspective you look at it from. And that's the problem, because that's not an accurate classifier. So how do we change this? How can we, wrap around this? So this is where we use something called the kernel trick, where if you look at this, kernel is kind of, the function it applies itself to. So let's look at something right here. I think this explains it super well. And how the kernel trick works. So we have 2 points that are, x1 and x2, which we can think of from the whiteboard perspective. We can think of it as this is x1, I guess this is x1, and this is x2. So we have, x1, x2, and then this function is e to the power of negative x1 minus x2. This is squared, so actually ignore this landmark. We're not going to talk about that. This is x1 squared, and this is 2 sigma squared. And the x1 and x2 is basically, this is actually false. I cannot label this as x1, x2. x1 is a point, and x2 is a point. They're actually all vectors, like I talked about earlier. So maybe let's pick this one as x1 and this one as x2. Okay. So what is this, double bar right here minus x2 representing? What does this mean? This is the magnitude. All right. And this magnitude is actually the Euclidean distance between the two. What is the Euclidean distance? Euclidean distance just means the closest possible line you can draw. You can imagine I draw some dotted lines right here where this is like, A, this is B, and this is C. You can actually think of it as the hypotenuse of the right triangle created by these two distances, or by these 2 points. Okay? So this is what this is, and then we divided this by 2 sigma squared, and then e to the power negative. So this sigma parameter is changeable. You can determine this. You can adjust this and things will change. And I'm going to show you exactly what's going on. So this explains it. Like I said, it's just the distance between 2 points, and they denote it as d12. So now, if this distance right here is really, really close, what's going to happen? So let's talk a little more mathematical. Let's apply a little more math into this, where we have, so x1 minus x2 and this squared. This is very small. Okay, so then e to the power negative, some very small value divided by 2 sigma squared. So when the top value is really small, the whole value on the top becomes really small. So it's just necessarily e to the something of very small. And when you raise something to the negative power that's really small, it's getting arbitrarily closer and closer to 0, right? So it's essentially really approaching e to the negative 0. I'm going to use some notations here, but this is going to be 1. So that means that if these two are very close to one another, and this value is getting really close to 1, that means that these 2 points have very similar traits. They're very similar in terms of their properties, and they're probably fall into the same category. All right. So what if this distance is super big? Then we have this is, really big. So then we have e to the power something negative big over 2 sigma squared. Like I said, this just translates to e to the negative something big. And what's going to happen is this value, it's becomes super, super negative, right? It's like writing 1 over e to the something big. And 1 over e to the something big is arbitrarily going to approach the value of 0, right? It's going to be 1 over something really big is going to be 0. Just like this right here, 1 over e to the something really small. We have, well, yeah, e to the negative 0, which is just 1. But anyways, where it's going to approach 0, that means that these two values are actually very far away from one another, and they're not similar at all. They're probably from two different categories, So, with discussion of that, then let's look at this diagram right here, which we have drawn. So, this is a region of similarity, okay? And the region of similarity is determined by your sigma. That's essentially what you use as a judgment to similar. So I can adjust the sigma value and say, oh, what if I extend this, and then maybe even here and here they fall under the same category. But regardless, let's talk about just this case right here, where x1 and x2, they're super close to one another, so they're going to fall into the same category. Okay. And then you can actually expand sigma, make sigma super big, and then you'll say, oh, okay, now this is where the region of similarity, they've expanded the region of similarity, and more things, even if you're slightly farther apart, it would still be classified as the same category. Okay. So what that brings to us is we essentially draw, let me actually draw this where I use their chart. I think that chart is better because it's 2D. It's easier to understand. Whereas something like this, and then this is the region of similarity, similar, and then we'll just say this is different, and this is also different. And from this top chart right here, which I will actually draw again because that was a poor, I should have deleted that before I recorded this. But let's say I have something like this and this ring around it. What's going to happen is, like I talked about, how these distances right here, especially these red clusters, they're very close to one another. They're very close to one another, and we pick kind of this red point as like the central point to decide how close these points are to one another, right? And you'll notice that all these red points are going to fall somewhere along this curve. Okay? And the green dots are, if we pick the correct parameter for sigma, they're going to fall somewhere on the outside of this. So I hope this image is starting to become more clear, where if you fall outside of this, it's because your distance is very far from what we discussed to as this is what is called a landmark. It just basically means like the point of focus, or the point that you choose to compare the distances to. Okay. In which case, I guess you could say I'm fixing an x1 or fixing an x2 and compare all the other values to that specific x1 or x2, depending on which one you fix. So now there's a very clear separation where I can slice, did not mean to use green there, where I can slice this region of similarity. I can slice this like a plane and slice right across this and say, okay, this falls into one category, we'll call this A, and both of these two fall under the category B. All right. And how does that look like when I actually slice this on a 3D scale? This is the 2D scale, and I think it's still a very good representation, but if we look at this picture right here, this is kind of like the clump that I drew, and where we pick the landmark to be somewhere center right here. That's why you see that as you see that it's getting very, very high when it's getting closer to the center. The center points are really close to one another, right? So of course it's going to really high. And then do you see how it draws this? This is what's referred to as a decision surface, where it slices across here. And this is also another good picture where you see two clear clusters, and then you use the Gaussian radial basis function, and it'll slice across this plane right here, and it'll create two separate groups. And that's what kind of this 2D drawing is. I think this 2D drawing might actually be a better representation than this 3D drawing because this is just easier to understand. So now we have solved the problem where, we have this cluster right here, and we can draw this plane that separates this, and it slices this, and then we can have this category A, and then this green category is B. Okay, so that's the essence of the radial basis function, which is, if you look at this, they use this by default because this is a fairly generally one of the better methods to do this. There are a lot of different kernels you could use. Um, you can look them up. There's like I said, there's polynomial, there's sigmoid, and then there's a bunch of other stuff that you could use. Very interesting topic there. And then you kind of just want to morph or pick the one that's best fit for the situation that you're in. So that's pretty much all I wanted to talk about in terms of today. Oh yeah, but next week I'm gonna be working on. So I actually attempted the Titanic uh project again. I couldn't. I did get a slightly higher score, and I did do most of it myself, with obviously looking some stuff up. But I think the biggest problem that I'm running into right now is definitely the data manipulation part. Filling in missing data and understanding when to scale or not scale the data. That's one of the things I'm going to look into next week. So next week's goals, we're going to be. Uh, so I'm actually going to mark this down actually. Uh, so scaling data, and essentially I'm going to ask why do I scale data and when do I scale data? So why/when. Um, Another thing is I want to the last 2 weeks, or maybe even three, I've been talking a lot about classification. Uh, yeah, classification methods, but I want to go into regression. That's why I'm going to do this. This is the housing data. I know I talked about attempting this last week, but there was actually I had quite a bit of stuff going on because it is getting close to finals week. It's like the last couple weeks of the semester, so I have to catch up on some work. Um, but the housing data, I want to manipulate the data quite a bit, and that does have like 40 columns of data. So I'm gonna try to do that, and next week I'm gonna present it and run over my thought process during the project, what I changed and why I did what I did. So I'm gonna do that. And like I said, the Titanic got a slightly higher score. It wasn't super impressive because I'm having a problem manipulating some of the data and filling in missing data, which I don't know what is the best way to fill in such missing data, and just stuff like that. So also, I do want to talk about this week. Kind of just been applying to some random jobs here and there. It's not that big of a deal. I'm not expecting to get anything because my major doesn't. Well, my major is somewhat related because it's pretty stat focused and stuff like that. But I'm not expecting to hear from much from it because I don't really have a lot of projects or experience under my belt. But just applying here and there, so maybe get an interview or something if I get lucky. But yeah, that's about it. So next week, focusing on these two topics, and then I guess learning uh, more regression uh, algorithms. Yep, that's what I'm going to be working on. So yeah, I will see you guys next week.